In the early 1900s, mathematicians and physicists were very interested in the shape of space. New experiments and theories were being developed that would ultimately create relativity theory and change our entire view of the universe. One question that it raised but could not answer was, what is the shape of the universe? Does the universe extend indefinitely in all directions? Perhaps it curves back on itself, so if we were to travel far enough in any given direction, we would be able to return to our original starting point but never turn back. Or perhaps the universe has a boundary, so if we go out far enough, there really is a definitive end to the universe. Today, this is still an open question. Mathematicians realized that they needed new tools to study the problems arising from these new theories. Although these kinds of questions are geometric in nature, Euclidean and analytic geometry, as one studies them in high school and college, are too localized and too rigid to adequately address them. So they developed a new way to define closeness that would be independent of any kind of a fixed measurement system. In the process, they created a new field of mathematics called topology. Topology can be thought of as a more general and a more global version of geometry. So where geometry looks at measurements such as length, area, and curvature, topology looks at more global properties of the entire space such as dimension or cardinality, connectedness, and orientation. We can think of topological properties as those that are preserved under shrinking, stretching, and redistribution, as long as we don't disrupt the essential closeness of nearby points. Mathematicians also like to classify objects and know when they are equivalent under certain properties. If two spaces are topologically indistinguishable, we say that the spaces are homeomorphic, and we can define a map between them that preserves the topology. That map is referred to as a homeomorphism. So for example, any object that we can create from this blob by shrinking or stretching it will be topologically equivalent to the solid ball. However, the solid ball and the blob are not homeomorphic or topologically equivalent to the solid torus, because in order to create the whole, we would have to puncture the blob, and that puncture would disrupt the essential closeness of the points that are nearby to that specific point. In particular, topologists are very interested in special spaces that are called manifolds. Manifolds are spaces that locally look like Rn, where R0 is a point, R1 is a line, R2 is a plane, and R3 is the familiar three-dimensional space that we live in. So if one zooms out far enough, a manifold may be curved or bounded, but at least on a local scale, it will look like standard Euclidean space. Some of the simplest topological properties are those of dimension, boundary, connectedness, and compactness. Dimension is heuristically the number of directions in which one can move and can be described mathematically as the number of parameters needed to specify a location within the space. A boundary is a definitive end where one has to turn around and come back. Connectedness intuitively means that the space is in one piece. If a space is disconnected, we consider the components that are connected separately and we classify it in terms of each of the connected components. Compact spaces are closed and bounded. Intuitively, this means that the space can be contained within a finite region and does not extend forever in any given direction. These are examples of connected one-dimensional manifolds or curves. The line segment is compact and has a boundary, so when the ladybug reaches the end point, if she's walking on the line, she has a definitive end where she has to turn around and go back. The real line and the helix are not compact and they have no boundary and they extend forever. The circle and the trefoil knot have no boundary, but they are compact. So for each of these four spaces, the ladybug that is walking on the topological space can walk forever in either direction without ever encountering any kind of a boundary or wall. However, on these two spaces, she can walk and never repeat her path, where on these two spaces she eventually will. This is actually enough to topologically classify all curves. If it has no boundary, it must be topologically equivalent to either the line or the circle, depending upon whether or not it is compact. So the line and the helix are homeomorphic, and the circle and the knot are homeomorphic. The only difference is how they appear to us, because they embed differently in three-dimensional space. In 2 dimensions, the complexity increases and new information is required. To this end, we introduce 2 new topological properties, the Euler characteristic and orientation. The Euler characteristic is represented by the Greek letter chi and is a formula that connects the number of vertices, edges, and faces of a polygonal tiling of a surface. For example, on the plane, we can draw any polygonal cluster, count the number of vertices, count the number of faces, and counting the entire exterior of the cluster as one face, and the number of edges, plug into the formula and determine the Euler characteristic. For the plane, this number will always be 2 regardless of the polygonal cluster that you choose. Now for a compact surface such as the sphere, we normally tile the entire surface of the sphere, and the straight lines are geodesics, which for a sphere means great circles. The sphere also has an Euler characteristic of 2. A second property is that of orientability. An orientable surface is one where you can pick a starting point, take any path, and return to your starting point with the same orientation. If even one path exists where you can return mirror reversed, the surface is non-orientable. Okay. So let's look at some examples. The plane is a non-compact orientable surface that has no boundary and has an Euler characteristic of 2. The cylinder is a compact surface that has a boundary on the edges, an Euler characteristic of 0, and is also orientable. The sphere and the torus are both compact surfaces that have no boundary, and they are orientable, but they have different Euler characteristics. The next 3 examples are of non-orientable surfaces. The simplest and the most common is the Mobius band, which is the non-orientable analog of the cylinder. To understand the non-orientability, consider a ladybug that begins walking on the Mobius band in this particular location with this particular orientation. If you carefully walk the ladybug around the entire surface of the Mobius band, once you come back to your original starting point, she will be mirror reversed from the orientation of which she left. Now, the key to understanding this is to recognize that as a mathematical object, the Mobius band has no thickness. So once she gets back to this point, she is at her original starting point. Now to us, the Mobius band appears to be sided because the fabric that is used to represent it does have a thickness to it. But as a mathematical object, you can think of her as being essentially inside of the fabric. So if she is inside the fabric, then when she comes back up on herself, these 2 positions represent the same location, even though in our physical representation they appear differently. So in this context, the ladybug is able to start off in this orientation and return to her original starting point and be mirror reversed. This is an example of non-orientability. It also shows that in some sense the Mobius band is one-sided because there is no place on the Mobius band that the ladybug cannot get to. By contrast, a cylinder is essentially two-sided because if the ladybug starts off on this side, there is no way that she can get to the interior without crossing the boundary, which is not allowed. Similarly, if she begins on the inside, there is no way that she can get to the outside without crossing that same boundary. Another example of a non-orientable surface is the Klein bottle. Now the Klein bottle does not actually exist in three-dimensional space, so that we have to improvise. So in order to construct the Klein bottle, we can take a rectangular piece of material and assume that this is something that is flexible and can bend and can bend as we need it. So the first step is to take the rectangular piece and glue up the long edge together to form a tube. Now at this point, if we were to take this tube, this cylinder, and wrap it around and connect to the edges in this fashion, we would have the torus. However, the ends, these circular ends, need to be connected in this particular fashion, which is impossible to do in three-dimensional space and be able to retain the seam that's along the tube. So this object does not exist in three-dimensional space. Instead, what we do to improvise is to draw it in 2 or 3 dimensions as having this point of self-intersection. Now this point does not exist in 4-dimensional space, which is where the Klein bottle actually embeds. So if the ladybug were living on the surface of the Klein bottle as a manifold, once she reached this apparent point of self-intersection, she would not notice that this point is here. So she would be able to walk along the neck of the Klein bottle and be able to keep walking down into the bell of the bottle, be able to reach this edge where the 2 pieces of the cylinder connect, be able to come back up the edge smoothly and walk what to us would appear to be on the inside of the Klein bottle and come back to this point. Now once she reached this point of self-intersection again, she would not notice that this neck is here because from her perspective it would not be. So once she reached this circle, she would be able to continue back again inside of the bell and be able to continue along the back side of the bell of the bottle, reach the bottom, and be able to turn around and come back and be able to go back up the neck of the Klein bottle. So this is another example of a non-orientable surface. The final example of a non-orientable surface is also compact and has no boundary, and it is referred to as the projective plane. This object also does not exist in three-dimensional space, so it is normally represented as 2 circular caps that are smoothly connected along the circumference, but a line of self-intersection that goes from the center and extends outward to the circumference. So if the ladybug were to live on the projective plane in 4-dimensional space, that she would be able to traverse the outside or the inside of the projective plane with no walls and no boundaries. As to the point of self-intersection, once she reached this line, if she were traveling from the upper right, she would be able to continue on to the lower left and never notice any kind of a seam. And also, if she were to be traveling on the outside from the upper left, once she reached this point, she would continue on the lower right and again never notice any kind of seam or disruption in her walking. So this is another example of a non-orientable surface. Okay. We can also create new topological spaces by gluing together old ones. So for example, we can take 2 one-hole tori and glue them together and create a 2-hole torus. We can also take 2 projective planes and glue them together to create a Klein bottle. This is actually enough to classify all 2-dimensional manifolds or surfaces that are compact and do not have a boundary. So if we have a compact surface that does not have a boundary, it must be homeomorphic to either the sphere, a connected sum of tori, or a connected sum of projective planes. So once you know whether or not your surface is orientable, and you know how many holes your surface possesses as counted by the Euler characteristic, then you automatically know which one of these surfaces your particular surface must be homeomorphic to. Things become more difficult once we go up to 3 dimensions. Besides just having the increased complexity of having an extra dimension, now we have the added problem of a lack of visualization. In order to adequately have a bird's eye view of a 2-dimensional object, you need at least 3 dimensions. So when able to externally view a 3-dimensional object and really understand its nuances, we need at least 4 dimensions, but we live in 3-dimensional space, so this is impossible. To get around this as much as possible, mathematicians will use implicit and parametric equations and study these equations that describe a given object. Topologists have also developed different kinds of identification procedures that do have the advantage of being independent of any kind of a fixed coordinate system. However, there are some tools that are available to us to help us visualize a three-manifold. So consider yourself and consider the room that you are currently sitting in. Now imagine your room has glass walls, a glass floor, and a glass ceiling, and your room is situated inside a grid with an infinite number of copies of the exact same room that you're in. So what happens when you look directly in front of you? Do you see a copy of yourself from behind? And if so, do you have the same orientation or are you mirror reversed? If you were to look down through the floor, do you see the top of your head? And if so, does your head have the same orientation or is it mirror reversed? Now we can also increase the complexity a little so that perhaps you look up through the ceiling and instead of seeing the bottoms of your feet, perhaps you see yourself from the side, and maybe instead of seeing yourself directly on or mirror reversed, perhaps you're rotated 90 degrees. So we can create different manifolds by taking the cube and identifying various faces of the cubes with varying degrees of rotation. We can also use the same procedure for polyhedra other than the cube and identify different faces together. Henri Poincare was a French mathematician who was very interested in relativity theory and in topology. He knew that a key to classifying three manifolds was correctly counting the holes. So he devised a new tool to do this called homotopy theory, which centered on the concept of a fundamental group. And a fundamental group essentially counts the number of distinct loops you can construct on the space that start and end at the same point. He was able to show that if two spaces were homeomorphic, that they had to have the same fundamental group, but he could not determine whether or not the converse was true, meaning that the fundamental group alone would be enough to classify homeomorphic spaces. These are examples of some fundamental groups. Now, a key to constructing these fundamental groups is to understand that whatever space you're working on, the loop, the string that's creating the loop, has to lie essentially in the space. Now for us, we have this ambient emptiness that's surrounding the space, but that the space that we experience is not part of the actual topological structure. So consider, for example, the real line. So we can take any point that's on the real line and we can identify that point and we can construct any loop we want that begins and ends at that point, and the loop can be as complicated and as long as we possibly want it to be, as long as it begins and ends at the same point. Now on the real line, there are no obstacles to encounter, so if we were to take the string and pull it back, we can always shrink this loop down to a single point. Now this will occur at that point P for any string that we choose, any loop that we choose. Furthermore, it's not just isolated to this particular point. Any point on the real line that we choose, we can always take this loop and shrink it down to a single point. Because this happens, we say that the fundamental group of the real line is trivial. Now, by contrast, the circle has a much more complicated fundamental group than the line. So if we think of the circle as being represented by this loom, and if we start at this point here, if we were to construct a loop beginning and ending at the point that had this type of structure to it, this particular loop can be pulled back to a single point and have the string remain entirely on the circle itself. However, if we were to take the string and make a complete revolution around the circle and then were to come back, that we can take and we can shrink this excess part of the circle, of the string, and be able to come back to here, but we cannot shrink the loop that begins and ends here, that traverses the circle at least once, without going off of the circle and into the ambient space in the middle. So this particular loop cannot be shrunk down to a single point, so it is distinctly different from the situation we had with the line. So in this particular case, the circle has a fundamental group that corresponds to the integers, and in essence, it is counting the number of complete revolutions that the string makes around the circle. And we can consider it with positive and negative, as the positive loops, say, being in the clockwise direction, and the negative loops being those in the counterclockwise direction. A similar situation happens when we go on to two-dimensional surfaces. So if we think of the surface as the plane as being represented by the piece of paper, then any particular point on the piece of paper that we pick, we can take a loop that begins and ends at the same point. No matter how complex the loop is or how long it is, it can always be pulled back and shrunk down to a single point. The same thing happens for the sphere, so these two both have trivial fundamental groups just like the real line. The cylinder has the same fundamental group as the circle because in essence you're counting the number of revolutions that the string makes around the circular girth of the cylinder. The torus has a fundamental group of z cross z, and in this particular case, the first z is essentially counting the number of loops that the string makes in this direction around that center hole, while the second z is counting the number of loops that the string makes in this direction around that center hole. The Mobius band has a fundamental group that's the same as that for the circle and for the cylinder, and the projective plane has an odd fundamental group that actually consists of only two elements. In this particular case, it turns out that what matters is how many times your string, when creating the loop, wraps around the center point. So in essence, if the loop wraps around the center point once, it's going to get entangled in that center point and it cannot be shrunk down, so it will remain as a full loop around that point. However, because of the non-orientability of the surface and not having a boundary, in this particular case, if it laps around twice, then the second time is going to essentially undo that entanglement that the first time around the center point created, and those particular loops will actually shrink down to a single point. So in essence, the fundamental group is counting whether the number of times that you wrap around that central point is if it wraps around an even number of times or an odd number of times. Poincare's experiments led him to believe that the fundamental group alone could not classify all compact three manifolds, but he thought that it might work in a special case. In 1904, he conjectured that if a compact three manifold had a trivial fundamental group, then it had to be topologically equivalent to the three-sphere, which is the simplest compact three manifold without boundary. His hunch was correct, but it would take 100 years to prove. The first development came in 1919 when James Alexander found some examples of two topological spaces that had the same fundamental group but were not homeomorphic to each other. So he was able to show that the fundamental group alone was not enough to classify three manifolds. However, the examples that he used did not have the trivial fundamental group, so he did not disprove the Poincare conjecture, which is just that special case. So the first real proofs in this direction came in the 1960s when three men were able to show that higher dimensional analogs of the Poincare conjecture were true, but the case remained unsolved for three-dimensional manifolds and four-dimensional manifolds. So four-dimensional manifolds, the analog of the Poincare conjecture, was proven in 1982 by Michael Friedman. Around that same time, Richard Hamilton and William Thurston came close to proving the original conjecture for three-dimensional spaces using very different approaches. However, each man encountered obstacles using his approach and was unable to prove the actual conjecture. Finally, in 2002, Grigori Perelman was able to build upon the work that Richard Hamilton had established with Ricci flows. It was able to get around the obstacles that Hamilton faced and prove that the Poincare conjecture was true. Poincare almost single-handedly developed the field that we now call algebraic topology, and in the process introduced powerful mathematical tools to study topological spaces. So proving his conjecture is true is a step at classifying all compact three-manifolds and identifying possible shapes for our universe. For those interested in more information, these books all contain information on the Poincare conjecture that is aimed at a general audience. The first two books by Devlin and the first and third book by Devlin and Stewart each contain chapters that deal specifically with the Poincare conjecture, while the middle book by O'Shea deals with the Poincare conjecture by itself. The last book by Jeffrey Weeks does not deal specifically with the Poincare conjecture, but it talks about visualizing higher dimensional manifolds given the limitations of the three-dimensional world that we live in. For those that are interested in more technical information, there's the specific statement of the problem can be found at the website for the Clay Mathematics Institute and also found in the AMS publication that was authorized by the Clay Mathematics Institute. For information regarding these specific notations and the specific ideas and concepts that deal with that go into creating the Poincare conjecture, those can be found in any good textbook on algebraic topology.